For our final project in CSCI 4050U, Shawn and I decided to take a look at the dataset Sign Language MNIST that's provided on Kaggle at the link above. This dataset is a collection of images of different American Sign Language signs for different alphabetic characters. The data in this dataset consists of both training and test data, of which there are 27,455 cases of training data and 7,172 cases of test data. Each training and test case represents a label 0 through 25 as a one-to-one map for each alphabetic letter A through Z. Now, it's important to note that there are no cases for letters J or Z due to these letters requiring gesture motions. Every case has a header row of label and pixel 1 through 784, which represent a single 28 by 28 pixel image with grayscale values between 0 and 255. Now for the problem at hand. Deaf and hard of hearing individuals have limited means of communication and interaction with others and with their smart devices, as verbal communication is not a feasible option for them. As such, in our final project, we aim to look at how neural networks may provide additional methods and accessibility options for deaf and hard of hearing individuals to communicate. Now, for our design, we'll be making use of CNNs, which stands for Convolutional Neural Network. We chose this neural network because they're specialized for analyzing visual information, which is going to be great for us, considering that our dataset is a collection of images. Now, in our model, we're going to be using the following layers and techniques in our design. Convolutional layers, obviously since we're using a convolutional neural network, max pooling, batch normalization, and dense layers. In our design, we chose to use convolutional layers because they're a core feature of CNNs. Now, this convolutional layer works by basically taking an input tensor, which would be an image, alongside a kernel tensor, which is a filter, and then applies a convolution formula that generates an output tensor that can describe the image. This is done by applying the kernel to patches or subregions of the image, and once you calculate the convolution, you slide the kernel across to the next patch based off a provided stride, which would be the number of pixels to shift. A quick demonstration has been provided here in which the kernel is applied to the blue shaded region of this input tensor and then produces the blue shaded region of the output tensor. Now our model is going to be applying 3 convolutional layers. Each convolutional layer is going to have a filter of size 64, 32, and 16 respectively, and they're each going to have padding equal to same, and their activation is going to be ReLU. As for pooling layers, these are pretty similar to convolutional layers in that they take a fixed shape region and slide it over all patches of the input image based off its stride, and then compute a single output for each patch. However, the difference is that these pooling layers don't have a kernel, so they're only going to return a single value from the values that are overlaid by the pooling region, in this case, the maximum value. In this example here, we have a 2x2 max pooling window, which is going to be applied to the blue shaded region of the input tensor, and then basically just return the max value of that section, which would be 2. In our model, we're going to be applying 3 max pooling layers throughout, and they're going to be applied after each convolutional layer and batch normalization. Each max pooling is going to have a pool size of 2x2, and they're going to have strides set to 2.
Something we learned outside of class that we're going to use in our design is batch normalization. And we'll be applying this after every single convolutional 2D layer in order to normalize the data. And this way, the model will be able to work with small values from 0 to 1, which stabilizes and speeds up the network. And we'll also be applying it right after the first hidden layer as well. And as for our dense layers, we are applying 2. We have a dense layer that's hidden with 512 units and a ReLU activation. And our final dense layer is going to be our output layer which has 28 units and softmax activation. As for our implementation, we'll be using TensorFlow, as we're familiar with that from class. We're going to be using that for building, training, and testing our convolutional neural network. And we'll be using functions like conv2d, max pooling, and batch normalization. As for reading our data and for analyzing our model, we'll be using pandas and matplotlib. And for testing image instances, we'll be using Pillow in order to open the image and do operations on it. Now I will demonstrate the functionality of our solution. First, I'll be evaluating the model with the test data, and then I'll show you an example of some specific instances that I have tested. Okay, so we ran the model. These are the results we got from running it this time. Quite high. Okay, and let's run some test data. So here we're just going to run the test data given to us by the data set. Okay. And then we're going to just get some random samples that were predicted by our model. Okay. So for the most part, the predicted class is the same as the actual class. The class in this case just means like the letter of the alphabet. So yeah, this one's looking perfect this time. So now we're going to be testing specific instances of sign language images. And what I did is I used pictures that I took of my own hand in the signs A, B, and V. And I took them with my phone, transferred them to my computer, and scaled them down to 28 by 28. And I'm reading these from Google Drive, so I transferred those scaled down images into this instance folder, and I named them A, B, and V. So I'm using Pillow to open the images and grayscale them. Then I'm going to be using as array from NumPy to convert the image into an array, and then after that I'm just going to flatten it to make it one-dimensional. And then I'm just going to put all these image arrays into this instance array, and then I'm going to normalize the pixels so they're in a small value from 0 to 1, and I'm just going to reshape the data. Next, I predict the instances using the model, and I end up getting these predictions, and unfortunately it looks like it's not predicting these properly. Oh yeah, so how this loop works is I have the actual classes, and here I'm just going to be comparing them to the predicted classes. So here are the predicted ones that I predicted, and then the actual classes I hard-coded because I know what they are. So the zero class is going to be A, 1 is going to be B, 21 is going to be V. And I think that this is due to overfitting, why this doesn't work. We had pretty high scores for the training and the validation and the testing. Training validation was like 99, testing was 93. So it isn't an overfitting issue. You could even tell that like the bias because if you look at the type of images that are being used, there is a lot of contrast in these images. You can see the blacks are a lot more defined compared to the images that I took myself. So I'm sure if I took images that were more similar to the test data in terms of the contrast, I probably would have had a higher chance of achieving a good match. So in summary, the training performance was around 95 to 99% effective. The testing performance was slightly lower at 85 to 95%. Validation was usually quite high at 99%. The accuracy and loss along the way was slightly unstable in early epochs, but it quickly converged. And nearly all sign language images from the test data were effectively classified to the appropriate alphabetical labels. But as for specific instances, they were not classified correctly. I tried, one time I ran the model, I got class 1 or the letter B matching properly, but that's just one time I ran the model from before. In conclusion, convolutional neural networks are great for image recognition, and as such, they can be used to accurately determine different sign language signs from large sets of images, and this has great potential for being implemented into apps and devices so that the input from deaf or people who have trouble hearing can have another option to communicate with their device. And here's the matrix for their team member contributions.